Hello everyone. We'll be starting with module number 3, Dynamics of Fluids, in which mainly we have Bernoulli's principle. We'll go into the details of the syllabus also. Okay, here there is a syllabus. Module 3 has got Fluid Dynamics Introduction, what it is consisting of in general. Then particularly we'll be going through all these points, that is forces acting on fluid in motion, Euler's equation of motion along a streamline, and Bernoulli's equation, assumptions and limitations of the Bernoulli's equation also. Then modified Bernoulli's equation, problems on applications of Bernoulli's equations with and without losses, momentum equation, problems on pipe bends. Then application wise introduction, then there is Venturi meter, orifice meter, then pitot tube. We'll be going through all these things step by step. Okay, what is meant by dynamics of fluids? First of all, the word dynamics itself, you should understand that it is totally different from statics. In statics, we have seen that the body is in stationary condition or it is in motion with a constant velocity. I repeat, in statics the body is at stationary condition or it is moving with a constant velocity, means there is no acceleration. There is no acceleration, that itself means that sum of the forces acting on the fluid or the substance or the object is equal to 0. In dynamics it is not so. The total sum or the resultant of the forces that are acting on fluid will not be equal to 0. So it is an accelerated motion. That is what we are going to study. That is what is dynamics. As far as statics is concerned, we have studied statics as well as kinematics also. In kinematics, geometry of motion is studied rather than the forces which cause the motion will not be studied, right? So here it is a dynamics of fluids flow. What it is, whenever some fluid is flowing, it is acted upon by a number of forces, obviously, to cause that motion. Now, study of motion of fluid mass, considering the forces acting on it as well as energies, the forces as well as energies involved in the flow, is known as dynamics of fluids. So major equation that comes into picture is F equal to ma. Okay. Anyway, F equal to ma is the major force which will be linking force as well as motion, because motion consists of acceleration and then the force which is causing the motion is F. They are linked through this equation, right? Okay, we'll go further. Now, what are the forces on the fluid mass that we have to consider? The bifurcation is quite simple. There are 3 headings under which they can be classified, and very simple to remember also. You can start from this end: line forces, area forces, surface area forces, and volume forces or body forces. So body forces means volume is involved, surface forces means area is involved, and then line forces means it is along the line. Now we'll see one by one. body forces or volume forces are proportional to volume. The examples will make it very clear. The weight. Weight is a gravitational force. Now how do you find weight? If you remember the equation involved for weight, it is W is equal to M into G or gamma into volume. That is what the equation that we want. So volume multiplied by unit weight will be giving you the total weight. Means volume is involved. Centrifugal force, magnetic force, electromotive force. So all these are involved with volume. That's why these are called volume forces or body forces. Next is surface area forces. Now these are proportional to area of contact. The best example is pressure, stress, turbulence, compressibility, etc. Because you know that pressure, you have already worked with a lot of things. So pressure multiplied by area will be giving you the total force. So the area force is involving the surface area force is involving area into consideration. Then the last one is line forces. This is proportional to length. The simple and best example is surface tension. You know that surface tension is denoted by sigma. The unit of measurement is Newton per meter length. So it is obviously depending upon length. Now if you want the total force because of surface tension, the force will be equal to the sigma multiplied by the length. We have used this equation a lot of times while proving droplet, etc., the size of the droplet in inside pressure, etc. We have seen that sigma is multiplied with the circumferential length there. So anyway, surface tension multiplied by length indicates a line force, right? The line forces are depending upon the length. Okay, now overall what I want to say here is it is forces means the force is a vector. So if you got two vectors in the same direction, they can be added together to get three. Like two is this way and suppose one is the other way around, the difference will be acting as a resultant, right? And such resultant should be taken and equated to MA. If there are two forces which are perpendicular to each other, as shown here, 3 is this way, 4 is this way, and 90 degrees angle. So to say, you have to find the resultant of this, which is 5, and then what is the angle made by this 5 with respect to this or with respect to that force, that you can find. Anyway, it has to be reduced to a single force, the resultant force, and that has to be equated to MA. That's how the analysis goes, right? Force is a vector, that has to be kept in mind. So variety of forces are there in case of fluids, so to say. Now next, okay, according to Newton's law, just now we have seen F equal to ma or sigma F equal to ma. Why we call it as sigma F? Because it is a resultant force that we have to consider. That's why it is always put as sigma F, because it is not a single force that we are talking about. There will be number of forces. All the forces have to be reduced to a single force, which is known as a resultant, which is represented here by sigma F, and that has to be equated to ma. Moreover, as it is a vector, you have to apply the equation direction wise. So if you want to apply the equation in x direction, sigma fx equal to m into ax. Ax is the acceleration component. You have studied a lot. Acceleration component in x direction. Similarly, sigma fy equal to m into ay. Fz is equal to maz. Az is acceleration component in z direction. Like that, we have to apply the equations in the particular direction. Okay. Now, what are the forces which are involved? The forces acting on the fluid are, here we have gravitational force, simple to indicate, F with a suffix G, pressure forces, F with suffix P, shear forces, that is because of viscosity, that is you can call it as viscous force also, or shear force, right? Whichever is convenient. It would be better if you call it as viscous force, because technically it will be referred to as that, right? So it is a viscous force, Fv, turbulence force, Ft, compressibility force or elastic force, force due to elasticity of the fluid, that is Fe, surface tension force, that is F with a suffix St. Compressibility force will be predominant in case of air or gases, but as far as liquids are concerned, this will be almost zero, right? Anyway, there are Fg, Fp, Fv, Ft, Fe and Fst, right? There are so many forces. Now all the forces put together, it is called resultant force. So we have sigma F, which is equal to Fg plus Fp plus Fv plus Ft plus Fe plus Ft. So this gives you a resultant force which is involving six forces in all. Now to remember that, the forces are, you can take the first letter GPS, because it is a shear force, so GPS, and then TCS, turbulence, compressibility, and then surface tension. So fluid forces can be GPS and TCS. Gravitational force, pressure force, shear forces, preferably called as viscous forces. Then we have turbulence, compressibility, and surface tension. Okay, these are the forces. Now, with these forces, what to do? Okay, now for sake of simplicity to study with, we can say the FST and FE are negligibly small in general cases of liquids, especially, right? Surface tension as well as uh, elastic forces or compressibility forces are negligible. Now, if you leave these two, then the remaining forces should be equated to MA. So you got gravity, pressure, viscous, and turbulence forces. If you consider all these forces and then equate to MA and then analyze, this equation is known as a Reynolds equation of motion of fluids. Okay. Now further, still simplification you can do for viscous flows, means for laminar flows, viscous flows in the sense, in the case of laminar condition, laminar flow, turbulence forces are neglected. Because turbulence is neglected, then one more term disappears. You'll be having sigma F equal to Fg plus Fp plus Fv, which is equal to Ma, and this particular equation is very familiarly known in fluid mechanics area as Navier-Stokes equation, very famous equation as far as fluid mechanics is concerned. Navier-Stokes equation, which will be involving three forces: gravity force, pressure force, and also viscous force is involved, right? Even further simplification is done in neglecting viscous force also. If viscous forces are neglected, then the total force becomes just summation of gravity and pressure forces, and none of these can be neglected now. Now this particular equation, right, Fg plus Fp is equal to Ma, if I put it as, is equal to Ma, and then try to analyze. This equation is known as Euler's equation. This is Euler's equation of motion. So Fg plus Fp in x direction is equal to max. Fg y direction plus Fp in y direction is equal to may. Fz z plus Fpz equal to maz. It is in k direction or z direction. So this is what is the simplification after neglecting uh, not so important forces. Now, what are the names of the equation? How they are called? Reynolds, Navier-Stokes, and then finally Euler's equation of motion. So equations are to be applied direction specific. That is what it is, right? So whatever we have done here, the same thing has been told over here. Okay. Now acceleration is involved. So we know this term. One term, if you know, you can reproduce all other terms. If you remember, ax is equal to dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. Check it, it's fine. Everywhere there is u. First term is differentiated with respect to t. All others have got x, y, z, and then corresponding multipliers as u, v, w. So this equation, if you can able to remember, that's well and good. Otherwise, you have to recall. Now, this part of acceleration, which is represented by dou u by dou t, is known as local acceleration. And that which is represented by all these three terms, which is spatial variation, which is called as convective acceleration. Convective, convective, convective acceleration. Okay. Now this equation itself is denoted as dou u by dou t is fine, plus this whole thing is written as v into dv by ds because it is a spatial variation. So acceleration in general is kept as dou v by dou s dou t, dou v by dou t, actually it should have been v, okay, so or dv by dt plus v into dv by ds. That is what is acceleration is, right? So I'll write it once again here. A can be written as, first is differentiation with respect to time, so dv by dt, that is first term, general first term that is indicated by first part, which is a local acceleration, plus convective part of the acceleration will be v into dv by ds. Okay, we'll be using this in the next slide also. Okay, here I'll try to erase these things because okay, Euler's equation of motion along a streamline. This is important now. Along a streamline. Now here I have shown one streamline just like that, just a streamline, right? A very small portion is considered of length ds. You can just see that length is ds, and there is a stream tube considered with the cross-sectional area dA, right? So here also it will be dA only, though it is shown slightly with a different size, but a very small magnitude. It is exaggerated in scale. Because of that, it is a tube with a same diameter, you can say same size. So dA over here also. Okay. Now what is the force which will be causing the motion here? Force which is acting on this surface will be equal to P into dA. You can remember that Euler's equation is consisting of what forces? Euler's equation is consisting of gravitational forces and pressure forces. There are two forces, right? Sorry, I'm not able to write it properly, but gravitational forces are involved and pressure forces are involved. So we'll be considering those two forces here. So pressure force which is acting on this area will be equal to the dA multiplied by P. So that is PdA. And for this area, it will be again dA the area multiplied by the pressure. The pressure now will be changing in a distance of ds. That's how do I write P plus dou P by dou S, the rate of change of pressure with the direction, multiplied by that ds, right? Rate of change with respect to direction into uh, say length into length. So that gives you a pressure, change to pressure multiplied by dA gives you the force. So these two forces are along the line ds. You can just see here there is a line, so this is the direction of ds, which is making an angle of theta with vertical, right? Angle theta with the vertical. Here also it is shown theta. Now pressure forces are done. Now what are the gravitational force? Gravitational force is nothing but weight of the fluid. So now W, the weight of the fluid, which will be given by the density multiplied by G, that is gamma. So this term now indicates gamma multiplied by volume. Volume is area multiplied by the length. So dA ds indicates volume, rho g indicates gamma. So that's why it is weight. So weight is equal to, just now earlier some slide I told you that W is given by gamma multiplied by volume. So gamma itself is written as rho into Z multiplied by volume is dA ds. Okay. Now by Euler's equation, Fg plus Fp is equal to m into A. Okay. Now here m is given by dA ds into rho, mass. Mass is given by volume multiplied by density. Acceleration is given by, already we have seen that it is v dv by dt plus v into dv by ds. That is the acceleration. Now one more analysis that you should see here is the angle theta is with respect to vertical. So this vertical part dz becomes ds cos theta or cos d theta, and horizontal one becomes ds sin d theta, but we'll be using this term just to make it convenient for you to recall afterwards. Okay, now further, now we have this equation Fg plus Fp equal to ma. So that is what I am writing here. What is the gravitational force? This is the one, that is dA ds rho g you have, right? And then instead of ds, what is written? Ds cos d theta it is written, because here I am taking a component of W in the direction of P, right? See here the weight is vertically acting. This angle over here is d theta we have taken. The component along this will be equal to W cos theta. So that's why, so this term indicates W multiplied by cos d theta. So that is the force in the direction along the streamline, right? The total weight multiplied by cos d theta, that is the force, and which is running down I have taken minus, right? That is the only thing. The other component will be perpendicular to that, which will not be contributing as far as ds is concerned. Okay. Now next forces are these two pressure forces, PdA minus again this one minus P plus dou P by dou S into ds into dA. So this is left hand part of the equation, that is Fg plus Fp is equal to mass. Mass is dA ds rho. Acceleration is given by v dv plus v dv by ds plus dv by dt. So I have just substituted everything over here. Now the simplification part. Here everywhere the dA is common in all the terms on the right hand side as well as left hand side, and once dA term go off, you will be left with that PDA minus PDA, that also cancels off first of all. So this term goes with this term first of all. You'll be left with only this dou P by dou S, ds, dA cancels off. So you will be left with only minus rho g cos d theta minus dou P by dou S, these terms cancel off, is equal to rho into dA ds goes rho into acceleration term. Now or the same thing can be written as this term, if I take it on one side and then make all the negative, or take all these things on the other side. So the equation becomes after division of rho, I think I have divided by rho with all the terms. So this goes off, this also goes off. Here there will be an extra term of 1 by rho. So we'll be left with V into dV by ds plus dV by dt, fine, plus g cos d theta, this rho is cancelled, and minus, plus because it is on the other side. So 1 by rho is an extra term for this, dou P by dou S equal to 0. Okay. Now for steady flow condition, so there is a condition that we have put so that further simplification can be made. Steady flow, what is that? Steady flow means the variation with respect to time is not there. So dou V by dou T or dV by dt term is equal to 0. So this term disappears from the equation. So we'll be left with 1 by rho dou P by dou S plus g into cos d theta. These terms ds added up on the top and bottom for adjustment. Now plus you have v into dv by ds equal to 0. Now by adding ds above and ds below, this bottom ds can be taken off. So you'll be left with dou P by rho plus z dz, because you can just see here ds cos d theta. So ds cos d theta is nothing but dz plus v dv equal to 0. So this particular form is known as Euler's equation along a streamline. So many a times in the examination they will be asking you to derive this equation. So you should know, you should be able to draw the figure. There are 2-3 things that you should remember: how to find out mass, how to find out acceleration, and then this particular substitution, ds cos d theta equal to dz. And we'll be always talking about along the direction of the streamline, the forces are added or subtracted depending upon the directions. So this PDA is added minus the weight component minus this pressure component. All that has been done here. So you can practice a couple of times. I think it will be easier for you. So this is Euler's equation of motion. Okay, it's a differential form of Euler's equation. Okay. Bernoulli's equation. Now it is very simple. See, integrate Euler's equation. Look at the starting point. Dou P by rho plus z dz plus v dv equal to a constant. Yes or no? Because if you just look at the earlier one, what it is. Now if you integrate this 0, obviously you should have a constant. Okay, that's why. So integrating this term, what we get is Bernoulli's equation. So starting point is Euler's equation. I should have written once Euler's equation first and then integrate it. After integrating, what you get is dou P by rho z dz under integration v dv equal to a constant, not equal to 0. Find it. In Euler's equation, it is equal to 0. Only Euler's equation will be equal to 0. But when you integrate that, integration of a 0 is obviously constant, because vice versa. If you differentiate this, it has to be 0. Right? That's all. So first equation is Euler's equation. and then integrate that Euler's equation to get Bernoulli's equation. Now if you simplify, for incompressible fluids, rho is constant. For incompressible fluids, rho is constant. So now if you integrate, keeping rho as constant, so it will be p by rho, because dou p integrated p by rho, plus g is held as a constant, so integrate dz is z, plus v dv, it is v squared by 2, is equal to a constant, or divide the whole thing by z, acceleration due to gravity, so p by rho z plus z, that is z, plus v squared by 2z is equal to a constant, right? Equal to a big constant c, right? So rho into g is nothing but gamma, so p by gamma plus z, that is z, plus v squared by 2z equal to a constant. This is Bernoulli's equation. Okay. Now here, most important thing is what are the terms that represent. The first term, which is p by gamma, and also we'll see units also. P by gamma is pressure head. You know that because you remember that P is equal to gamma H. Yes. Now what is H? H is equal to P by gamma. That is, H is nothing but pressure head. So that is what this term is. So pressure head or pressure energy per unit weight of the fluid. This is most important part. Per unit weight of the fluid. Now what is the pressure energy? Gamma H. Per unit weight means you have to divide by gamma. So that you will be left with H. That is what it is. Now this Z or Z, which is a potential energy head per unit weight of the fluid. Potential head is Z or Z. Similarly, V squared by 2Z is a kinetic energy per unit weight of the liquid. So it is called kinetic head or velocity head. So all these three parts of the Bernoulli's equation are nothing but heads. Pressure head, this is a potential head or datum head, it is also called as. This is velocity head. Put together, it is a constant. What is the meaning of constant? Means if the flow is occurring like that, and then if you consider energy of flow per unit weight at a particular point, and then if you go further at some distance and then pick up fluid and measure the energy per unit weight, it is not changing, it is remaining the same. That is what is constant, right? It remains same, there is no change, the total energy remains same. So it is nothing but conservation of energy principle, in short, right? The form is different so that it is applicable for fluids. Now further, this P by gamma plus Z, this term is known as piezometric head. Piezometric head. The equation is applicable for ideal fluids because there is no loss in energy. I have told you this can happen only ideally speaking, otherwise there will be friction, there will be loss of it, but with an assumption that it is ideal fluid, there is no loss, hence the equation is valid. But for real fluids where there is a friction, there is a viscosity, there has to be a loss. So how it is done is, if you call this point as point number 1, and then if you call this point as point number 2, now total energy at point 1 can be P1 by gamma plus V1 squared by 2Z plus Z1. So all these terms with a suffix 1, 1, 1. So it is nothing but energy at this level. Flow is occurring this way, and then at the point 2, obviously it will be losing some head. So if I just equate it to P2 by gamma V2 squared by 2G plus Z2, this term will be obviously less by an amount that the head lost from 1 to 2. So that's why that head loss term is added, so that this equation becomes, it becomes an equation. Equal to sign will be in between. So this is HL. So now this form of Bernoulli's equation is known as modified Bernoulli's equation, which is applicable for real fluids. Otherwise, a plain form of Bernoulli's equation, which is P by gamma plus Z plus V squared by 2Z equal to constant, is applicable only for ideal fluids. If you want to make it applicable for real fluids, you have to introduce HL into picture. So HL is nothing but energy loss between section 1 and 2. You can call it a section or point. It is along the flow. You have to choose a reference section 1 and section 2, or point 1 and point 2 in the motion. So obviously downstream end means after some flow the energy will be bit less because the head is lost. So this is Bernoulli's equation. I think with this we'll stop. Thank you.